So guys, till now we have studied about the temperature distribution inside the plane wall and inside the hollow cylindrical pipe. Now we will see about the hollow sphere. Hollow sphere. So consider that there is a hollow spherical shell in which inside of it some liquid is boiling, and when then that liquid is boiling, its temperature is constant, and because of that constant temperature it will maintain the wall temperature also constant while it is in contact. Okay, so the wall which is contact in the cylindrical wall spherical body like that. So assuming that T1 is more than T2 and this inside surface is maintain a temperature T1 by some means, and this as temperature T2, and since T1 is greater than T2, heat will flow outwards. Okay, okay, so similarly if we see at any if we see the cross-sectional view of it like the one we did for cylindrical pipe, so this is inner radius r1, this is in outer radius r2, and this is the solid material, and this is the inside surface, this is outside surface, maintain a temperature T1 and T2 respectively, and this is the location at any arbitrary radius r. All right, so and this arbitrary surface is maintain a temperature T at any theta, right, at any theta, because we are considering only one dimensional heat flow, only radial heat flow we are considering, one dimensional, as we said the assumptions before, radial heat transfer. Fine, so if we see at any r, just for the sake of understanding, consider two planes, one on left and one on right of this yellow plane. So whatever heat is coming from the inside as Q, same heat will leave from this right side plane, red plane. Why? Because inside this small distance there is no heat generation at any point, and also the condition is maintained at is steady. It means there is no change of the energy of the system. Because of that there is no change of heat flow, and because of and because of the no internal heat generation, there will not be any addition of the heat flowing through these two planes. Okay, so there is no function of Q as function of R. Q is not function of R. Okay, mind that, it will be used in the derivation. Similar analysis we can do for cylindrical also. That's why we could take out the Q out. Let's see here, we could take out the Q outside because Q is not function of R. Okay, so let's start from the Fourier law. Similarly, minus ka dt by dr, again integrating, and put a as 4 pi r square for the spherical case, k times 4 pi dt, k and all 4 pi all are constant. Integrating is from t1 to t, r1 to r. Fine. Then q can be taken out by this analysis, so we will get like 1 by r minus 1 by r1 after integration, q k times 4 pi times t minus t1. Okay, this is the first equation. Again integrating this above equation, let's say it is a, integrating from r1 to r2 means similarly from r1 to r2 we will get 1 by r2 1 by r1 minus k times 4 pi t2 minus t1 is equation 2. Dividing these two equations we can get the temperature profile. If you remember the mathematics of high school, this is the equation of hyperbola. So it means the temperature profile inside the hollow sphere will be hyperbolic in nature. T1, T2, hyperbola. It is a temperature, it is a radius R1, this is a radius R2. Similarly, as we did for cylindrical case, we have to find the thermal resistance for the hollow cylinder. So using equation 2 and rearranging it, we can get like 4 pi k t1 t2 minus t1 r1 minus r2 r1 r2 t1 minus t2, because t1 is greater than, so write it like this. Okay, this is r1 r2, write in the form of temperature drop, so t1 minus t2 divided by 1 by 4 pi k 1 by r1 minus 1 by r2. If you rearrange the above equation, you can get like this. So again it comes out to be thermal resistance for the hollow sphere to be 1 by 4 pi k times 1 by r1 minus 1 by r2. This is the thermal resistance for the case of hollow sphere. Okay, so Similar kind of analysis you can do for any kind of body. So as an exercise, um, I'm giving you one problem that derive all the above two cases for cylindrical and for sphere by using governing equation, and using boundary condition derive using governing equation. Okay, and the second problem is, let's say this is a conical pipe and it is insulated from its lateral sides. This is the second problem, and this surface is maintained at temperature T1, this surface is maintained at temperature T2, and this is one dimensional heat flow. Okay, and this surface is at x1 distance from some reference, and this is at x2 distance from some reference, and I am saying that temperature is some function of x, and I am giving you the distribution of the diameter of this a times x. A is constant. So find the temperature distribution. Temperature distribution and also heat transfer. Okay, for this case. Next, we will see the hollow cylinders in series and sphere in series. Thank you.